Hello everyone, my name is Brian Light. I'm a principal consultant with Automotive on our threat management team. I specialize in application security, so web applications, mobile applications, and IoT. Today I'm going to be talking about a fun project of mine that deals with a little hardware, a little reverse engineering, and cars. To give you a bit of background, I am a car guy. I have a 1994 Audi S4 that I've had for several years now. I'm passionate about older Audis, prestigious motorsport history, and some folks might not know, but their all-wheel drive systems, their quattro systems, really gave them a name in the late 70s, early 80s, because they were involved in motorsport called rally, where you race on loose surfaces like gravel or tarmac or snow, and all sorts of surfaces around the world. And Audi came out with all-wheel drive in rally motorsport. In that time, it disrupted the field because most of the cars were rear-wheel drive or front-wheel drive. And after Audi came out with all-wheel drive, they started dominating competition, and pretty much every other manufacturer had to develop their own system to compete. But beyond that, beyond the history of the car, the engine is particularly unique, and it's a 5-cylinder, so it's a relatively small 2.2 liter turbocharged engine, but it has very unique design relative to some of the other common designs, 4-cylinder, 6-cylinder, 8-cylinder that you see. On top of that, it's got a 5-speed manual transmission and actually a locking rear differential, which is very odd for a passenger car. So it's unique, it's relatively rare, and I just love the way these things drive, and I'm an enthusiast about them. So a little about me. I live about 30 minutes west of Denver. I live probably around 8,300 feet or so, and as you may know, Denver's about 5,280, a mile-high city. You'll see why I'm talking about elevation, because it becomes more important as part of the theme of what I am modifying in the ECU as part of this presentation. So for my goals on this car, I wanted to add approximately 100 horsepower with upgraded turbocharger. And that is just the start of it. There's a lot of things that need to be modified in order to actually handle that increase in power. And it is a lot, but it's not unprecedented for these engines to be able to handle. But among the changes that adding a larger turbocharger brings is modifying the software on the factory control unit, unless you would like to get an aftermarket control unit to program yourself. And in order to use the factory control unit, which I really wanted to do, I had to reverse engineer it, since there's no intended way for Bosch Motronic to go ahead and allow consumers to modify the factory stock parameters. And I'd like to start off as well by just saying I have a huge credit to PRJ, who did quite a bit of foundational work. As I found out during the course of my initial reverse engineering and analysis of the CCU, I found out partway through that he had done this foundational work to really create a tuning suite, and he released it several years ago because it is no longer really financially viable for him to create tunes for people, but he wanted to support the community. So I am building my work, branching my work off of his, and doing my reverse engineering and modification in areas where either his was incomplete or I wanted to explore further into this engine control unit to be able to modify additional things that were not supported. So as an overview, what we'll be talking about is a little bit of tuning theory. I don't want to get too deep into it because I know not everyone's a car person. specifically for modifying the target boost compensation at high altitude. And now what that means is the amount of extra air pressure that the turbocharger is delivering to the engine has to vary. And especially at altitude where I live, and we have mountains up to mid 14,000 feet. We can drive up to the top of one of them, not too far from Denver, so our elevation varies quite a bit, and turbochargers are affected significantly by altitude. Not all tuners actually wind up compensating for that appropriately, because it's one of the last things on the list for them to really modify, especially since most people live at lower elevations, and it's not a factor that really comes into play all too often in the United States or the rest of the world. For the hardware analysis, what we'll be talking about is this engine control unit that's in the picture. So it is a Bosch Motronic unit, the version 2.32. The layout of this, I'll go over. There's a top and a bottom board with several system on chips and several external pieces of memory. So I'll go over what those look like and what was involved in extracting those. From a firmware analysis perspective, I'll go over specifically, because there's so much here to go over, I could never cover it in an hour. But to cover just one workflow, I will show how I was able to look at the code for altitude compensation and how I was able to modify parameters to be able to better compensate for the turbocharger that I have. So I'll start with tuning theory. For engine fundamentals, I'll try to keep this as simple as possible. The engine needs these things to operate at a very basic level. What it is an air compressor. So as pistons move up and down, they compress air, and air is composed of roughly 20% oxygen. Oxygen is required for a combustion reaction. To actually ignite that combustion reaction, you need a spark plug on a gasoline engine. It's possible to have the compression go high enough to ignite the mixture or to have other problems, but I won't go into that. For instance, diesels work to ignite their fuel by compression. So in this case, gasoline combines with air, and you need to combine it in the right proportions. That mixture of air and gasoline is compressed, and then the spark plug ignites it at just the right time. For turbocharger fundamentals, that's more what we'll be focusing on for the ECU modification. The turbocharger is also a big air compressor, so it helps add air into the engine, and the more air you can add, the more power you can make, because you can inject more fuel and essentially increase the displacement of the engine by shoving more air into it, and that's one of the reasons we call it forced induction. But a turbocharger fundamentally works by having a positive feedback loop, whereby pressure from the exhaust feeds pressure into the intake side. Now they're not directly connected other than through a shaft, but the pressure from the exhaust flow drives a compressor on the inside, on the intake, which then forces more air. So the more exhaust there is, the more intake there is, and so it's a positive feedback loop in which this compressor can add air into the engine, increasing it above the atmospheric pressure outside, which, depending on what elevation you're at, varies quite a bit. As far as tuning theory at altitude goes, it's important to note one particular thing about turbochargers if you know nothing else. This is called the pressure ratio. Turbochargers fundamentally work on the relative pressure that they're trying to compress versus the amount of pressure available outside and the atmospheric pressure. So this map in this image is called a compressor map. It might be a little daunting to look at, but on one side, the vertical axis, you have a pressure ratio. And on the horizontal axis, you have airflow. And even if you don't know what those numbers are relative to anything, as you go farther to the right on the horizontal axis, it's essentially more RPMs for the engine. As the engine is revving up, more airflow is flowing through as the pistons are traveling faster. And on the left side is a description of how much the compressor or the turbocharger is trying to compress the air. And the less air that you have, the harder the turbocharger has to work, or vice versa. The harder you want the turbocharger to work to compress the air available, the more that it's going to be stressed. These little rings in the map refer to islands of efficiency, and we might see 0.76, 0.73, 0.23, so on and so forth. In the middle of the map is where the turbocharger is its most efficient, meaning that it has the highest charge density of fuel and air, not getting too hot as it compresses it, not wasting energy to create byproduct of heat as it works too hard. Technically, it can provide more power if it works outside of its efficiency zone, but where it works best for power, efficiency, and longevity is in those zones. But what tuners like to do is push the turbocharger to the absolute limits of what's possible. And oftentimes you'll see pretty impressive gains, maybe 40 horsepower with the same exact factory turbocharger. However, you're kind of pushing things to the ragged edge at that point. And if you forget to compensate in other ways, sure, you can have lots of power, but you might not be efficient, and you might be at risk of breaking things, or at the very least reducing the longevity of components. So let's get into the engine control unit. That image that I showed you a couple slides back was the control unit. This is the inside of it. We're looking at the lower board zoomed in on an EEPROM chip. This lower board has a system on chip, the Siemens 80535B microcontroller. Runs on the Intel 8501 instruction set using this EEPROM chip for external memory. So all the program code is actually on the chip right in the center of this picture. And you might see there's a little clear circular window, and you can see a chip right in the middle of that. That's because this is a UV erasable EEPROM dual inline package. And so it's possible to program this by hooking it up and applying the right voltages. But to erase it, you actually have to provide strong UV light, so it's kind of cool. It's an older technology. Most chips are electronically erasable and programmable, so you don't have to do that. So for this lower board, the functions are a little bit separated. It primarily controls the turbocharger. So there's essentially what's called a wastegate that controls how much the turbo can spool up, or if it dumps all of the pressure off to keep it from spooling up. In that way it can vary based on pulse width modulation to keep the pressure in the desired zone. We call that target boost. This chip also, this side of the board also handles knock control, which I won't get into, but it's very important, especially in turbocharged engines, for preventing destruction of the engine if there's a bad batch of gas. And technically if there's an issue with the tune, but the tune should not have any issues if it's been written correctly. On the upper board, there's also a Siemens 80535B microcontroller hooked up to an external memory chip, EEPROM. And this is a little bit larger. It contains more code for controlling the fundamental engine parameters of fuel and spark, warm-up, enrichment. There's a whole bunch of stuff in here. As far as the microcontroller goes, the 8051 language that it's written in is 8-bit. It integrates with external ROM, as we've seen in the other pictures. And on board this chip are multiplexed analog to digital converters. These are important for obtaining signals from various engine sensors, of which on this particular vehicle there are at least 50 combined inputs and outputs. So it's important to be able to receive lots of data and to process it quickly, as well as send data. In order to get the program memory to be able to tune this vehicle, what I had to do is remove those printed circuit boards, look at the EEPROM dual inline packages, and then desolder them from the board. Once I had physically removed those, what I did is I put a dual inline package socket for each side of the board, upper and lower. And that way, for any changes that I made there onto the EEPROM, I could just place them inside the socket or remove them instead of having to solder or desolder every time. Should be far too much work. In order to read the contents of these EEPROMs, I have a TL866, and these chips have their specifications printed right on them, which were fortunately supported by the reader. And once I attempted to read these EEPROMs, I was successful in dumping all the bytes out from them. At this point, I was able to do statistical analysis on the entropy of the file and just do an initial overlook into what the hex data looks like. I could see that it most likely wasn't encrypted and that all the program code was on this external ROM rather than any of the internal flash provided by the Siemens microcontrollers. Now, in modern engine control units, there might be encryption measures so that if you were to physically try and extract it in this way, you would be met with a big challenge in trying to actually decrypt them. There might be a dedicated hardware chip that performs cryptographic operations. But at the same time, on modern ECUs, there is the ability to update firmware and the ability to modify settings at the manufacturer or at the dealer oftentimes. And because the memory is electronically erasable, a lot of times there are protocols provided by the manufacturer that would allow tuners to try to choose a different approach altogether from the one I am choosing, where they would communicate with the ECU using the manufacturer protocol and modify the software without ever having to physically take it apart. For my purposes, this was required. An initial analysis of the ROM on these two chips was done with just looking at hex like I mentioned previously, but also primarily with reverse engineering using IDA. So even though there's a lot of functions in the ECU, I'll try to focus on altitude correction. Having analyzed the bin files in IDA, I was able to find where the main routine of each of these bin files was, but we'll just focus on the boost / knock control chip because that handles altitude correction. In the main routine, the altitude is read from the analog to digital converter. And I was able to determine that because I physically traced where the altitude sensor is, and it's independent from the other sensors on the vehicle. Where it is fed into the ECU on a certain pin, and where that ECU pin traces to on the analog to digital converter. And I can also see in the ECU software where that ADC value is being fed into a register, so I know that that routine is relevant to some kind of altitude correction, whether it be compensating for fuel or for boost. In this case it's boost because the chip doesn't handle fuel or spark, that's separate on the other chip. So after the altitude is read from the analog to digital converter, I was able to find where the boost control routine is. So where the turbocharger pressure control routine was being called. And that value for altitude was being used in the boost control routine to look up a value from a table, which itself is a subroutine that was very useful for analyzing how the software is getting values and how I can modify those values to modify the behavior of the ECU. This is a snippet from IDA that shows the main loop of the program. I have just a focused section on where the altitude is read from the analog to digital converter. The program then does a sanity check to make sure the sensor is not giving it an unexpected value that's out of bounds, either way too high or way too low. Maybe it's unplugged, it's basically error checking. And then lastly, there's a default value there if it does come back with an error. So it level sets, I think, at 3,000 feet. I'd have to go back and look at that one to see exactly what it is. After it reads that value from the ADC, the ECU then goes into the boost control routine and goes into a subroutine where it looks up values from tables. And it's pretty complicated and messy. It's messily written. I had written some pseudocode for it, but the high level function is that it gets the actual index from the table because it just provides a reference to a table, which in turn is a reference to other tables. Then on one axis of this table is the RPM, on the other one is the altitude. Then it actually looks up the correction value, and that's based on an interpolation between neighboring cells so that it smooths out the limited amount of space that there is in memory for you to store values versus the many minute environmental or sensor variations between those table values, and then it returns the correction value. This is fed into the boost control. The boost control on this first line has the table reference. It's fed into that map read we just looked at. So from, as we showed from that map read, you get back the correction value. So that lcall is a call to that read map function I've labeled. After that value is returned for correction, it's multiplied with the running value for target boost pressure. So that A times B and rotate left through the carry, what that's doing is essentially taking a running value for what the ECU thinks there should be target boost without any corrections, and then modifies it essentially by a percentage, maybe 80%, to reduce that pressure based on altitude. As far as the axis byte structure goes, there's a byte to designate the start of the axis, how long it is, how many values there are, and then how many, where the start of those values are. And because 8-bit is such a small space to represent values in, there's some tricks that the code does to actually calculate into a larger domain of values. So for those axis values, it's the summation of the previous values to actually get the real value of that row in the table, or the column in the table. So for row n, it's the summation of the previous values, which is calculated by the ECU. That way it only has to store a smaller value, because the maximum it could store theoretically is 256. The pictures I have here are from a program called TunerPro, in which I've done the reverse engineering and then actually plugged in that computation and a conversion factor as well, just to make it more legible for each of the axes and then for the table itself. So you have the altitude as the first column, and RPM is the second column, and then partial atmosphere, PATM correction, which is essentially high elevation. And the column is in kilopascals, the row is in RPM, and the values are percentages written as, decimal. And these are actually the updated values from when I modified it for my purposes, to make sure I wasn't overspinning the turbo and getting to a dangerous situation. So essentially, for the modifications, now that since I was able to reverse engineer how the program retrieves data from the sensor, then passes it to the turbocharger control program, then looks up the table values, I was able to figure out where the table axes were and the table values themselves. From that, I was able to plug it into a more easy graphical user interface where I could modify those values. And through an analysis of multiple data points, I was able to figure out what a reasonable correction factor was for those values in real-world numbers versus hex numbers. In doing that, I could finally modify these altitude correction parameters. So what I determined the main problems were here is that as we know, the target boost pressure has to go down as elevation goes up, otherwise the turbocharger might be overspun. But these values that I was looking at were actually from a European model with a different turbocharger. So even though these numbers would be appropriate for that turbocharger, they're not appropriate for the one that I'm running. They're too aggressive. And lastly, when tuners push the limits of a turbocharger, there's no room for overhead, and these correction factors have to be more aggressive to scale back the turbocharger pressure to compensate. Whereas with a factory tune, the compensation doesn't have to be as aggressive because there is more room for overhead and there's not as much of a loss of power at altitude as a result. So below we'll give some example target boost calculations. For my turbocharger, as you've seen in that compressor map, 2.4 is a pressure ratio at right in the middle of their RPM range is going to be really pushing it. And I'll use that as the basis for trying to prevent our pressure from going any higher, which would result in a higher pressure ratio. So our target boost is the value I'm going to try to solve for by using a pressure ratio at which I don't want to exceed. So at sea level, that atmospheric pressure is about 101 kilopascals or 14.7 psi. That means we can run 141 kPa of boost on this turbo, which is 20 psi. So 20 psi plus 14.7 psi. Yeah, I mean, we're talking about a very large increase in air that's being shoved into this engine versus what it would be able to do without the turbo. As we go up in altitude, if we were trying to still maintain that aggressive 2.4 pressure ratio, we would have to, because there's only 84 kilopascals of partial pressure, then we would have to reduce our turbocharger using that formula, our target boost. And now we're down to 117 kilopascals target boost. And the picture I have included is about an hour away from where I live, and it's a popular way to get to some of the ski resorts. It's about 12,000 feet, and the pressure is awfully low there. Anyone who's been up to Loveland Pass or in the high mountains of the Rockies will know just breathing is difficult. 64 kPa is the partial pressure, right? And so now we're at roughly 63% of the boost pressure at sea level. Now, in this slide, it shows the final results of those calculations and how it was appropriate to change it. It's a pretty dramatic difference. The one on the left is the original corrections, and the one on the right is the new corrections. So the original ones had the wrong turbo data, the wrong pressure ratio compensations, and it also was based on a factory tune that was more conservative, so there was more overhead to push the turbo harder at altitude, relatively speaking. And the new one is a calculation that drops the pressure pretty much linearly, and the main reason is because to maintain that pressure ratio while still pushing the turbo as hard as absolutely possible, you need to scale it down in a much more dramatic way. And this has allowed me to safely continue tuning. I have had a lot of fun with this. So I'd like to thank everyone for sticking with me. I appreciate it. I hope you all learned something today. I had a lot of fun with this project.